Welcome back. In this sublesson, we are going to talk about spanning tree protocol, how the spanning tree protocol functions, and what are the different flavors of spanning tree protocol, difference between STP and MSTP, and we'll learn about how spanning tree protocol helps build loop-free topologies. The spanning tree protocol, or STP, is a protocol that builds loop-free topologies in an environment by temporarily blocking traffic on specific ports. By blocking the ports, it ensures that traffic is not looped into the environment from all the ports which are into forwarding state. There are multiple versions of STP. The initial specification was defined in IEEE 802.1d, but then later more enhancements were done with PVST, PVST+, RSTP, which we call Rapid Spanning Tree Protocol, and MST, or Multiple Spanning Tree Protocol. NXOS supports RSTP as well as MST mode with the backward compatibility with the initial specification 802.1d. The original version of STP comes from IEEE 802.1d standard and provides support for ensuring a loop-free topology for one VLAN. In the spanning tree protocol, every port transitions through a series of following states. First, disabled. This means the port is an administratively off position. That means it's in shutdown state. Blocking. The switch port is enabled, but the port is not forwarding any traffic to ensure a loop is not created. The switch does not modify the MAC address table. It can only receive BPDUs or bridge protocol data units from other switches. Listening state. In this state, the switch port has transitioned from a blocking state and can now send and receive BPDUs, but it cannot forward any network traffic. Learning state. In this state, the switch port can now modify the MAC address table with any network traffic that it receives. The switch does not forward any other traffic beside BPDUs. The switch port transitions into the state after the forward delay has expired. Forwarding state. In the forwarding state, the switch port can forward all network traffic and can update the MAC address table as expected. This is a final state for a switch port to forward network traffic. Broken state. This state is not usually seen. It is seen only in scenarios when the switch has detected a configuration or operational problem on a port that can have major effects. The port will discard packets for as long as the problem continues to exist. Apart from the states, the spanning tree protocol consists of three different port types: the designated port, root port, and blocking port. A designated port is a network port that receives and forwards frames to other switches. Designated port provides connectivity to downstream devices and switches. A network port that connects to the root switch or an upstream switch in a spanning tree topology. Blocking port. A network port is not forwarding traffic because of STP. Let's go through some of the key terminologies which are relevant with spanning tree protocol. Root bridge. A root bridge is one of the most important switch in the layer 2 topology. All ports are in forwarding state on this switch. This switch is considered the top of the spanning tree for all path calculations by the other switches. All ports on the root bridge are categorized as designated ports. BPDUs, or bridge protocol data units. The BPDU is a network frame which is strictly used for detecting spanning tree topology. The BPDUs are required so that switches can identify the root bridge, root ports, designated ports, and blocking ports. The BPDU consists of the following fields: the STP type, root path cost, root bridge identifier, local bridge identifier, max age, hello timer, and forward delay. The BPDU uses destination MAC address of 0180C2000000. So if you want to capture BPDU packets in the network, you might want to be looking for the MAC address with destination 0180C2000000. Root path cost. The combination of the cost for a specific path towards the root switch. Root bridge identifier. Root bridge identifier is a combination of root bridge system MAC, system ID extension, and system priority of the root bridge. Local bridge identifier. The local bridge identifier is a combination of advertising switches, bridge system MAC, system ID extension, and system priority of the root bridge. Max H, the timer that controls the maximum length of time that passes before a bridge port saves its BPDU information. On Nexus switches, this is relevant for backward compatibility with switches using traditional 802.1d spanning tree protocol. Hello time. The hello time is the time that a BPDU is advertised out of a port. The default value of hello time is 2 seconds and can be configured to a value between 1 to 10 seconds. Forward delay. The forward delay is the amount of time that a port stays in a listening state and learning state. The default value is 15 seconds and can be changed to a value of 15 to 30 seconds. Rapid spanning tree protocol. Note that the NXOS switch supports RSTP. The RSTP is defined in IEEE 802.1w specification. This specification is an enhancement. The PVST and PVST Plus were Cisco's proprietary spanning tree protocols. The concepts of these protocols were incorporated with other enhancements to form the IEEE 802.1w specification, which is the RSTP specification. In the 802.1q specification, more enhancements were added for faster convergence. The RSTP protocol has 4 port roles: the designated root port, alternate port, and backup port. The designated port is a network port that receives and forwards frames to other switches. Designated ports provide connectivity to the downstream devices and switches. Root port, or the RP. A root port is a network port that connects to the root switch or an upstream switch of the spanning tree topology. Alternate port, a network port that provides alternate connectivity towards the root switch via a different switch. Backup port, a network port that provides link redundancy towards the current root switch. The backup port cannot guarantee connectivity to the root bridge in the event of upstream switch fails. A backup port exists only when multiple links connect between the same switches. This would usually come into play when we have a hub connected between 2 switches. With RSTP protocol, switches exchange handshakes with each other to transition through the following STP states. The first state is the discarding state. In the discarding state, the switch port is enabled, but the port is not forwarding any traffic to ensure that no loop is created. This state combines the traditional STP states of disabled, blocking, and listening states. Learning state. The switch port now modifies the MAC address table with any MAC address with any network traffic that it receives. The switch still does not forward any other network traffic beside BPDUs. The forwarding state is the state in which the switch port forwards all network traffic and updates the MAC address table as expected. This is the final state for a switch port to forward the network traffic. Let's now look at the finite state machine of how RSTP functions in a layer 2 topology. In this topology, we have 3 switches, NX1, NX2, and NX3. And NX2 is selected as the root bridge. Even though it doesn't have the lowest system MAC, it still behaves as the root bridge due to the defined priority on the switch. When the switch is selected as the root bridge, the ports connecting the downstream switches are selected or elected as the designated ports. On the downstream switches, the ports connecting to the root bridge are selected or marked as the root port because they are connecting to the root bridge. The other 2 ports that are there between NX2 and NX3, one goes to a designated port state and the other side of the link goes to an alternate state. Remember, both these ports are selected as designated and the other side is set to alternate. The reason being, we do not have any hub connected between these 2 switches. If there was a hub connected between these 2 switches, we would see them as alternate and the other port as backup. One important thing to note here is that the port elected as an alternate port is in the blocking state. Thus, it is not forwarding any network traffic. Let's now look at how the root bridge election happens. The first step with STP is to identify the root bridge. As a switch initializes, it assumes that it is the root bridge, and it uses the local bridge identifier as the root bridge identifier. It then listens to the neighbor's BPDU and performs the following task. If the neighbor BPDU is inferior to its own BPDU, then the switch ignores that BPDU. When we say inferior, it depends on the fact what is the system MAC of the device from which the BPDU is received. If the neighbor's BPDU is preferred to its own BPDU, then the switch updates its BPDU to include the new root bridge identifier along a new root path. This path is the total cost of the path in order to reach the new root bridge. This process continues until all switches in the topology have identified the root bridge switch. The spanning tree protocol deems a switch more preferable if the priority of the bridge identifier is lower than other BPDUs. The next step is locating the root ports. After the switch has identified the root bridge, they must determine the root ports. The root bridge continues to advertise BPDUs out to all of its ports. The switch compares the BPDU information to identify the root port. The root port is selected using the following logic. Remember, all these points that are listed here are going to be followed only when there is a tie in the previous criteria. At the top, or at the very first level, the interface associated to the lowest path cost is more preferred. The interfaces then, if there's a tie, the interface associated to the lowest system priority of the advertising switch is preferred. If there's a tie again, the interface associated to the lowest system MAC address of the advertising switch is preferred. If there's a tie in this case as well, in that scenario, when multiple links are associated to the same switch, then the lowest port priority from the advertising router is preferred. If there's a tie in that scenario, the final point will be preferred, which states that when the multiple links are associated to the same switch, the lower port number of the advertising router is preferred. In all, if you closely look at the spanning tree protocol, lowest is preferred. Whatever is the lowest, it is preferred to make the decision, be it the root bridge, locating the root ports, or depending on locating the blocked ports. Let's now look at how to locate the blocked ports in a spanning tree topology. The ports to be blocked on the spanning tree topology are decided using the following logic. The first criteria is the interface must not be considered as a root port. The system priority of a local switch is compared to the system priority of the remote switch. The local port is moved to a blocking state if the remote switch priority is lower than the local switch priority. The system MAC address of the local switch is compared to the system MAC address of the remote switch. The local port is moved to a blocking state if the remote system MAC is lower than the local switch system MAC. In NXOS, there are different port types. We have point-to-point, we have P2P peer, network P2P, and edge P2P. In the point-to-point, the port type connects with other network device. It can be a PC or another switch running RSTP. In a P2P peer port type, the port type detects that it is connected to an 802.1d switch and is operating in a backward compatibility mode. The network P2P port type is specifically configured to connect with another RSTP switch and provide bridge assurance. The edge P2P port type is specifically configured to connect with another host device. By another host device, we mean a laptop or PC. When we enable edge P2P port type, that means port fast is enabled by default. Let's now look at the different STP costs associated with different link types. If it's a 10 Mbps link, the interface STP cost is 100. For 100 Mbps link, we have 19. For 1 gig links, we have the STP cost as 4. For 10 gig links, we have STP cost as 2. And any link speed above 20 gig and faster, we have the STP cost set to 1. Let's now look at multiple spanning tree. In an environment with thousands of VLANs, maintaining a spanning tree protocol state for all the VLANs can become a burden on the switch processors. MST provides a blended approach by placing multiple VLANs on a single spanning tree protocol tree called an MST instance. The MST provides traffic engineering. In an MST topology, traffic engineering is performed by modifying the MST instance parameters versus modifying parameters on a VLAN by VLAN basis. There are a few terminologies that are associated with multiple spanning tree. First, MST region. The MST region is comprised of identically configured switches in an MST topology. Instance. An MST instance is a collection of VLANs that are mapped together in the MST topology. CIST. A CIST is a collection of ISTs, which means internal spanning trees, in each MST region. The CIST is same as an IST inside an MST region and same as CST outside an MST region. Regional port. It involves the root election process. In this, a root is identified for each instance in a region. M record. The M record holds spanning tree information for an individual MST instance. Apart from regular MST instances, there is MST instance 0. An MST instance 0 is a special instance which is used to create a single loop-free topology in the entire L2 domain. When connecting to other regions and versions of the spanning tree, the IST or MST instance 0 settings are used to communicate. The MST instance 0 is either responsible for being the root of all regions or for carrying information about regional roots inside the MST region. These are some of the basic fundamentals of spanning tree, rapid spanning tree protocol and multiple spanning tree protocol. We'll now look at how to configure spanning tree protocol and multiple spanning tree protocol on Cisco NX OS switches.